Oh, you started recording?
Yep.
Okay.
Can you share?
Yes, I should share and check. I should share desktop too. And let me start the presentation. Play slideshow.
Yep, that's perfect.
Okay.
Can you flip it one or two? Yep, that's fine. Perfect. You can stop sharing.
Yeah, I'll stop sharing now. And
quickly and get the charging. If there's no pin for charge, let's charge. This one is for charge, but this is for the.
this is for
Oh,
that
there's
one.
a place.
share the screen. And I'll start the hang on. Stop sharing. I think it got switched. No, but I need to see my presenter view. Okay, ठीक है.
First, then share.
I don't think I can go back to exit. I think first I have to share, then I have to,
Okay.
then,
Yeah, share the screen first.
where is the Zoom meeting? Okay, it's here. Share screen, desktop to share. Now let
Go to
me
keynote and present.
keynote
Just play.
play slideshow.
Right. Okay. All right.
You are unmuted, right? So you should come.
You should unmute here.
Yeah, this is unmuted.
Okay, perfect. So welcome everyone. Welcome to SAAO Colloquium. I'm in for Nargis.
I don't know.
No, I think people can hear. I tried that as well.
Okay.
Okay, and so today we have Siddharth. She's going to talk about FiberPol. Everybody knows Siddharth, but just for a reintroduction, Siddharth is a postdoc here, but before that, he did his short stint at University of Crete as a postdoc as well, after finishing his PhD at IUCAA. He is my office mate for last 7 years almost, except for 2 years in the between. So yeah, he is in a conquest to make polarimetry great again. So I'll just give him the podium. So for the participants online, you can type your questions the moment you like in the chat, and I'll ask questions at the end. And I hope you're going to finish it in 45 minutes.
I'll try to.
Thank you.
Yeah, thanks, Abhisachi. Yeah. So yeah, thank you everyone for coming, and I'll present this work that we have been developing, where we have been doing in the FiberLab. But before I start, it's going to be long 40 minutes talk, so you can interrupt me in between at any point, and we can have more like a conversation rather than me giving me a sermon here. And polarimetry is anyway something that not everybody does, so a lot of jargons and terms are maybe new to you, so please feel free to stop me in between and ask. Yeah, so we are developing this instrument / mode for SpUpNIC called FiberPol 60. I'll come to the 60 later, but FiberPol is probably more easier to comprehend, fibers and polarimetry. And this is a work that I've been doing with Sabyasachi and Matt here. Yeah, so I'll just get on with the talk itself. See a chat, I'm just wondering. Lisa, is it better now? Right. I'll take some water so that I can louder. Yeah, I don't know. Can others hear properly? Or you can hear from there. Okay. Yes, so wait. Yes, so I've structured the talk kind of in this, like, I'll start off with an introduction to polarimetry and how polarimeters work in general, and then give a scientific motivation for building FiberPol, how it works or how it will work when we get it ready, and also at the end some technical reasons why we want to build FiberPol, especially in the context of how it can be used for bigger telescope. Bigger telescopes like SALT or any other telescope. It's not telescope specific. So coming to polarimetry, polarization is like an intrinsic property of transverse waves, whether it's electromagnetic wave or even string waves. So every wave or pulse in transverse waves have a sense of direction of oscillation or vibration, right? So that's what polarization means at a base level. And individual waves are always polarized. So in the case of electromagnetic waves, if you have a wave propagating along the z-axis, then you can write the electric fields in x and y as sinusoidal functions, which with each having their own amplitude and phase. And if you do some calculations, you'll see that the overall polarization vector traces an ellipse. So that's called the polarization ellipse equation. So broadly, so I mean, what to summarize it, it's like the polarization state of an individual photon or wave can be written as an ellipse, and linear and circular polarization are the special cases of this general elliptical polarization. We have linear polarization when the phases of x and y are in sync, and circular polarization when they differ by pi by 2. But that's not what astronomers are interested in the sense that when we refer to polarimetry, we mean not for individual wave, but statistically, is there a preferred polarization state in a light coming from a source, right? So is there a pattern in the successive waves that come from the source? And to quantify this, we use what is called Stokes parameters. There are 4 Stokes parameters. The first one is just intensity, which doesn't capture any polarimetric information as such. But the remaining 3, Q, U, and V, are the ones that we are often interested in. Q and U are called the linear Stokes parameters, and we measure circular polarization. Circular polarization in optical wavelengths is usually 0, so we will ignore it for the rest of this talk. So basically, we are interested in measuring these 2 Stokes parameters, Q and U, through polarimeters. So how to measure it then? In principle, it's pretty simple. We need 4 measurements. So the experiment goes on like this. If you have any light source coming at an intensity I, we need to place a linear polarizer at 4 orientations, 0, 45, 90, and 135, and measure the output intensities that is denoted by I theta. So basically 4 measurements. And the Stokes parameter Q is just the difference between the intensity at 0 and 90. And Stokes parameter U, 45, the difference in intensity is at when the polarizer is at 45 and 135. Reasonably simple, I guess. And in astronomy, instead of just using a simple polarimetric filter, we use what is called Wallstrom prisms, which, so usual filters like this allow one polarization and block every other polarization when it interferes, when the light is incident on it. We can't afford to do that in astronomy because we don't want to lose light. So instead of blocking one polarization and letting other polarization pass through, a Wallstrom prism splits the light at different angles depending on the input polarization. So we kind of get both the polarimeter, we get the intensity for both polarization and also, at the same time. So basically, we can measure the 1 Stokes parameters at a time. And the reason to do it, as I said, is 1, so that we don't lose light, and the other being we mitigate a lot of atmospheric effects when we measure 1 Stokes parameters at a time. And so then you could just have 2 measurements, right? One with the halfway plate, one with the Wallstrom prism at 0 and 45, and just rotate the Wallstrom prism to 45 degrees, and you measure 45 and 135. But instead, for reasons of optical simplicity and as well as obtaining better accuracies, we use what is called a half-wave plate. A half-wave plate is a polarimetric device that helps us rotate the polarization vector. So instead of rotating the measurement apparatus, we rotate the polarization of the beam itself. So the way a half-wave plate works is, if we put it at any position and angle with respect to the beam, depending on its orientation, it rotates the polarization vector. So if we place the halfway plate at an angle theta with respect to the instrument, it rotates the beam vector by 2 theta, so twice of that. So to give an example, if we want to measure the Stokes parameters Q, which is on I don't think my mouse works, but the top right image. So we put the halfway plate at 0 degrees. There's no rotation of the beam, and we just simply measure the 0, 90 intensities, and that gives us Q, Stokes parameter Q. When we're interested in the Stokes parameter U, we place the halfway plate at 22.5 degrees, as shown in the bottom image. It rotates the beam by -45, and then we use the same Wallstrom prism and get 45 and 135 degrees intensities, and that gives us the Stokes parameter U. So basically, most astronomical polarimeters consist of a Wallstrom prism and a rotating half-wave plate in front of it. And in addition to just 0 and 20.5, we also make more measurements at 45 and 67.5, which are just to check the internal systematics of the instrument during the measurement and helps in calibrations. So yeah, that's broadly how polarimeter works. And this is how a science exposure looks like. This is one of the images that I often show during my presentation. So this is RoboPol. I don't know, maybe some people have heard about it. So this is an instrument that Professor Ramprakash, our thesis supervisor, had built some 10 years back. So here you can, each star, when it passes through the system, gets split into 4 beams corresponding to the 4 different measurements that is needed, 0, 45, 135, 90, at the same time, using, instead of 1, 2 Wallstrom prisms. So then we take this image for a star that we're interested in, calculate the intensities, that is photometry, for each star. So we get this I0, so I0, I90, 45, 135. And from that, using the equations I show, we can just calculate the Stokes parameters, Q and U. And the polarimetric angle and amount of polarization is just an algebraic transformation of these. Amount of polarization is Q and U added in quadrature, and the polarimetric angle is related to a tan inverse function of the 2 Stokes parameters. Yeah.
Measurement for I90 overlap with measurement for I35.
Yeah, that's the problem. So the RoboPol has been, when it was conceived, it was designed for point sources, and the large field of view came as a bonus. So for central object, there's a mask that ensures that even if there's a nearby object, you won't have one of the 4 spots interfering with the central.
The center object is masked.
Yeah, you can see the kind of darker in the, but for the field, it's a problem. And for example, if you see the top left, there are stars where there is intermingling. That is why for wall up, what we're doing is each of these 4 spots will go to a different CCD instead of these 4 overlapping on top of each other. That will take care of this overlapping of beams. And that's what also makes wall up complicated.
Yeah, so can you ask a question? Just repeat it for the.
Oh, right. I forgot. I now should tell the question and they figure out. Yeah. Okay. Any other questions? No?
Sorry, so if you don't worry about overlapping stars, so what's the difference in the final accuracy of the measurement of polarization between a star in the mass and a star in the field?
You mean, so this, of course, the sky background is 4 times higher at the.
Yeah, so what's the difference in the final answer?
I don't have, I mean, we know that, I mean, we conventionally don't do off-axis polarimetry in RoboPol because it has other problems apart from just background, in the sense that there's dust and all that. So I think at some point they did it and it was still around 0.1%, but I'm not sure whether we have tried to calibrate it now and see. But a higher background would, of course, lead to a higher photon noise-based errors. I think that's, if there were no dust, I think that would be the only difference. Provided we can calculate, we can.
What is the final
Number.
number of difference? Yes. Once you've done the extraction, the data reduction.
It was at 0.1% 10 years back, but I'm not sure.
Siddharth, yeah, can I jump in? This is Ram.
Yeah, sure. Ram is trying to answer it. I'll transmit to you. Yeah, Ram, go ahead.
The answer is the instrument systematic is low enough that anywhere in the field, almost anywhere in the field of 13 arc minutes by 13 arc minutes, we can get down to 0.1% polarimetric accuracy. It's just that in the mask region, you can reach this accuracy based on photon noise for a much smaller exposure time than in that mask region because of the higher sky background. But anywhere in the field, you can get down to 0.1%.
So you're saying it's 0.1% across the field of view? Yeah. Okay. Okay, if there are no more questions, I'll proceed. Why am I getting? Okay. So now I'll try to motivate the scientific reasons why we want to build something like a FiberPol. And I'll start with point sources and then go to extended sources, because that's where most of the polarimetric studies have been done so far. So starlight in general is unpolarized, and but when astronomers measure starlight polarization, they find that all stars are polarized. And that's mainly because there's interstellar dust that acts as an asymmetry creating system. So if you look at this cartoon sketch that I've taken from Costa's paper from 2015, so there's a background star that's unpolarized, and there's no preferred oscillation, electric vector oscillation. Then it passes through a dust cloud that has this asymmetric dust grains that is aligned along the magnetic field. It creates this asymmetry in the system where one polarization is systematically absorbed / scattered more than the other, which is the one that is perpendicular to the magnetic field. So the net light that is coming from the dust cloud after it passes through the dust cloud is polarized along the direction of the magnetic field. And the amount of polarization is related to the amount of dust as well. So when astronomers do stellar polarimetry, we actually learn usually nothing about the star itself, but more about the intervening medium that is there between the star and us on Earth. Yeah, so basically two parameters that we get: the angle of polarization, which is straight away the direction of the magnetic field, and the amount of polarization, degree of polarization, which is trace of the dust. And typically the amount of polarization is at 0.2, 0.3, maybe 0.5%. That's why polarimeters need to be built to the accuracy of 0.1% so that we get 2-3 sigma confidence in our measurements. And even going beyond just simple broadband, imaging polarimetry, where we get polarization value for just one wavelength. What's even more powerful is when we do spectropolarimetry of these objects, because we get this kind of plots, which is what we call Sikorsky curve, because Sikorsky is the first person who did all this. So you can see this pattern that kind of peaks at around 0.5 micron and then starts getting down. And we have found that across all sight lines in the diffuse ISM, this kind of equation generally works very well to characterize the spectropolarimetric curve. And the parameters that we get when we do this kind of fit, the lambda max, being the wavelength at which it peaks, is related to the shortest grains that get aligned with the magnetic field. And the other parameters that we get are straight away become parameters for dust modeling guys to create their dust model. So polarimetry is an integral polarimetric measurements from which we can infer dust properties are very integral part of the dust model that is there. And all dust models have to explain these measurements. Now, the thing is that we have done this kind of work in our galaxy for individual stars a lot. But what we have really not done is trying to get Sikorsky curve for galaxies outside of our own. So that's where 2D spectropolarimetry becomes very interesting, technical advancement, if we can do it. So the broad scientific question that motivates 2D spectropolarimetry, at least in my case, is to answer the question, what's the nature of dust, especially its interactions with the magnetic field in nearby galaxies, starting from Andromeda and other nearby galaxies. And we have not yet done that. I mean, people have studied does in photometry and spectroscopy in these galaxies, but not in polarimetry, in the optical wavelengths. Maybe in far IR they have done. So this can then inform the current test models and also test those models in these galaxies. And ideally, one would start to test this in different kinds of galaxies and different kinds of environments within the galaxies, star-forming regions, non-far, the diffuse ISM and all that. So to give a visualization of what someone like me would be interested in, for example, this is one of the most beautiful galaxies, the Pinwheel galaxy, which is a large spiral along with a smaller interacting galaxy at the top. For those who may notice, this is the salt finder chart, and the middle that you see is one of the long-slit modes that we often use. So, if we want to study these various parts of the system, we can imagine like we'll have to kind of scan through the entire system, right? And becomes inefficient for this kind of system for such external objects. And maybe we are interested in the center of the big galaxy, center of the smaller galaxy, and intervening regions in between. Rather than using salt long slit, more efficient way could be to just point individual fiber bundles, if we could do fiber-based spectropolarimetry, to these regions. And then we get, for each of these pointings, a 2D spectra of that joining region, right? So that's the kind of science that motivates FiberPol for us. Yeah, so now I'll come to FiberPol. So the idea is then to demonstrate and develop this kind of a capability on an existing spectrograph. So right now we have what is called SpUpNIC on the 1.9 meter telescope at Sutherland. Yeah, SpUpNIC is a conventional long-slit spectrograph that works in the entire optical wavelength range and has spectral resolutions going from low to medium resolutions of 500 to 5,000. And the top level concept is that we want to add a fiber-fed spectropolarimetric front-end capability. So without touching the spectrograph, without touching the telescope, somewhere in between, we want to introduce for lack of a better word, a 2D spectropolarimetric intelligence in the system. So the idea would be if we have a sky field like the one on the top, after going through the polarimetric system, it would be split into two images corresponding to 0 and 90 polarizations, or 45 and 135. And then this can be fed to fiber arrays. And these fiber arrays are then rerouted and fed to the spectrograph. And the spectrograph works as a conventional spectrograph, right? So the polarimetric encoding of the information has already been done beforehand, or decoding rather. So the reason we call it 60 is, if you could do something like this, we will get the two Stokes parameters Q and U / P and theta, polarization angular theta, as a function of wavelength, X, Y, and also the intensity as well. So that becomes a 6-dimensional data output. And it can also be a technology demonstrator for spectrographs on other large telescopes, including SALT, or even the ELTs. And I have a slide or two about it later. How that can be useful, but yeah. So, and the other thing is that because we are developing all this, we also wanted to have what is called a simple non-polarimetric IFU for people who may just want to do spectroscopy and not do polarimetry, because that's usually the dominant population in any institute. Does anybody have questions before I move on?
Will you be showing how the fibers go into the spectrograph?
Yeah. This is like giving what we started with as a top level idea and how the implementation is. I'll show. Are you checking in Zoom if somebody has a question? Okay. So the way SpUpNIC works right now is that we have this 1.9 meter telescope, this F18 beam that's fed to SpUpNIC, which takes F18 beam and creates a spectra for a 2 arc minute long slit. Now, what we want to do with FiberPol is have a polarimetric unit that will do all this polarimetric analysis. So we'll have actually two systems. I'll come to it slowly. Maybe I'll just go to the end slide first. So in between, we'll insert our what is called FiberPol system, and it does 2-3 things before the light is fed to the SpUpNIC spectrograph. First, it takes the F18 beam. It's then does the polarimetric separation into E and O beams with a half-wave plate and a Wallerstein prism. Then it speeds up the beam to a faster beam of f3.7 because fibers work optimally when the beam is fast. So we do polarimetric analysis and beam speeding up in what we call the focal reducer unit. Then it is at that point that it's fed to a bundle of two fiber bundles, which take these E and O images of the sky, like I've shown in below. We have a 20 by 10 actually. It's not 8, 10. After it goes through the reducer, it's split into these two E and O beam images for this field. And then the fibers are fed this image. And then, because the telescope still takes F18 beam, we use an expander system to so we use the fibers then to form this pseudo slit of 2 arc minute, but it's at 3.7. So we use the expander unit to speed up this 3.7 beam to F18, and then it's fed to SpUpNIC. So SpUpNIC doesn't know something has happened beforehand. And all as I said, the intelligence has been encoded after the telescope, but before SpUpNIC. I know that was a bit condensed, but I don't know how else I can say this. So now I'll go to individual steps. So we have this focal reducer unit. As I said, we have this F18 beam. So we want to speed up to F3.7. We do the polarimetric analysis at this step. I'll go into the detail later in succeeding slide. And we also want to have good imaging performance so that we don't lose spatial resolution capabilities. So we feed the fibers, and as of now, the fiber array has been designed for 100 micron fibers. There's a possibility to even go for 50 microns, but that's for later. Right now, we just want to stick to 100 microns. So yeah, once this has been done, it's fed to these two fiber bundles, pick up the light. So this will be the array. It's 5, 4, 4, this arrangement. So this two bundles of 5, 4, 4, 4, 5, 4. Take this light, and then it's formed as a pseudo slit, or like a 1D array of fibers at f3.7. And then it's fed to the expander unit, which speeds it up to F18 beam and also maintains good imaging performance. And then it's fed to SpUpNIC, basically. Yeah. Yes.
I don't understand the square block there. So there's two fiber bundles at the bottom for the lower.
Yes.
So at the top, you have another fiber bundle.
No, it's just the image of the fiber bundle on sky.
So the image is imaged onto what then? Or I don't know, you have a drawing of a fiber. You have 3 fiber bundles.
Yeah, so maybe I should. That's the input sky field. So imagine that's a detector. If you had a detector like that, how would it show on sky? So, okay. The fibers are just at the end. The top one is just, as Retta said, the footprint of those fibers on sky. I mean, you may have a bigger object, but you wouldn't pick off light from any other object, right?
I guess I need to see a hardware drawing and not a.
Yeah, probably this one drawing. You see it on the design. Optical design probably.
So yeah, maybe, but it's just that if we're going the other way around, in the sense that the fibers will pick up this object.
Fibers are actually looking below each other in the direction. There are two arrays of fibers for E and O. Okay, they are separated by the angular separation of the Wallerstein prism. The blue one at top, dark blue, is just that, those.
So-
The focal plane of the telescope is, for non-polarized light, is the footprint at the top. That footprint is split into two footprints for E and O. Each of those footprints feed the array of fibers.
Yeah, I get that part.
Okay.
I don't understand what's happening with the focal
Which focal?
plane. The telescope.
The focal plane of the telescope.
We're not reaching there, by the way.
is the new focal plane that I use. The new focal plane lies not so very much.
So, but the light goes to a focal reducer.
So even before it reaches the focal plane, we take it before it reaches the focal
It
plane.
goes to the focal reducer, and
Yeah.
then it goes to what?
Goes, yeah, it gets
Goes to the fibers.
it goes to polarimetric optics.
I think we should go on the optical design actually. Yes, it's.
Anyway, just before I go there, it needs to fit in, all this needs to fit in this box of SpUpNIC acquisition box. And it's a tight space, so a lot of hard work just went into making sure all this fits in here. Which is not much space. Maybe I'll just go to a design directly itself, the reducer. So I don't have a mouse, otherwise I would show it. So the first one at the top is what is a half-wave plate. So that's where the light is coming from the telescope, the F18 beam. So the first element in the entire optical system is the half-wave plate.
Black line at the top.
Yeah, the black line at the top. It doesn't affect the F number, of course. But there is a lens there which makes the F18 beam to an intermediate F number. Then it's collimated by a set of lenses, which is then fed to a Wallerstein prism. The diagonal, yes. That's where the beams have been split into E and O beams. No fibers here. And then there's a fold mirror because we need to compactify everything. And then it's fed to a camera system, which includes a chromat and a field flattener. And then the image is created of f3.7, F number. This is then fed to the fiber bundle here.
Oh, no,
Okay. So this is a polarimetry mode. I'm just trying to I'll go back to some slides and see if I missed anything. Nothing important, I think. Yeah, so the design consideration were, because it's a technology demonstrated, we wanted to use cheap and easily available optics. So everything in the design uses off-the-shelf Thought Labs optics and mounts and everything. The only, I think, custom thing we'll need is for the fiber bundles thing to make the fiber arrays, the associated mounts for that, which the workshop will make. But apart from that, everything is off the shelf. And the aim is to reach 0.1% accuracy or better, and hopefully we'll reach that because that's kind of the benchmark for most polarimeters. And we should reach that per spectral bin. And also, I think the other requirement is that we should be able to mount it inside the box and take it off so that other people can use a long slit mode when they want to use SAAO, right? So all those requirements and thoughts have gone into the design of the optomechanical and the optical system. Yeah, so and after the design, the specs are the following. It works optimally. The design works optimally for 400 to 700 nanometers. And because it's at the front end, it should work for all existing gratings, provided the wavelength coverage is not, some other grating, if there's a grating that works post 700 nanometers, I don't know how it will work, but any grating that can work inside SpUpNIC between 400 to 700, any resolution, it should work with FiberPol. So FiberPol works as a dual channel polarimeter. So we have one Wallerstein prism. So we'll get 2 images rather than the 4 that are showed for overpol. But that's okay. And we have a modulating half-wave plate at the top, as I said. Yeah. Also, as I said, we will provide an option to switch between polarimetric and non-polarimetric mode. So people, if they want to just use spectroscopic eye view, they can use that. And for that, there will be motorized in-out motion of a fold mirror that I will show. Yeah, and as I said, from either this spectroscopic or polarimetric unit, there will be these fiber bundles that come out and form a pseudo slit to be fed to the expander system that will that will create the input for SpUpNIC. Yeah.
Don't you have to motorize the beam splitter and the beam?
I'll show how. I'll talk about that. So this is what we saw. That's at a polarimetric mode, as in light comes and all that. So ignore that fold mirror there. This will go out of path. So ignore the fold mirror. So light comes and you get these fiber bundles for polarimetric mode now. Now, when you want to do non-polarimetric mode, we'll put a fold mirror there and ignore the later part, and the light will go to the spectroscopic arm. So once we inject this fold mirror, light is then steered in perpendicular direction, right?
So
There will be optics there. Yes. Yeah.
Oh, there it is.
But this is a missing link. This is what is needed, I think, in diagrams. Yeah. Yeah. These are technical information on spot diagrams, but let me just summarize that the performance is really good. That is again one of the challenges, to get good performance using off-the-shelf optics, and that's where a lot of my effort in optical design went. I mean, the field is small, that helps. It's not a really big field of view. It's like 20 by 10 arc seconds for polarimetric unit, but even then it becomes a challenge after a point. Yeah, so expander is also the same. So there'll be a common expander for both. So it will be like, there's one fiber bundle coming from the polarimetric arm. There'll be one from the non-polarimetric arm. They'll be put side by side, and depending on which one we want, we'll use that slit, and that is fed to the expander, and then that creates F18 beam to be fed to the instrument, which is SpUpNIC. Yeah, I think I'll skip this part, but again,
The expander is used by both.
yes.
So then you have to shift the fiber. No, but there's two parallel slits, and so when you're not using one beam, essentially one slit is dark.
I mean, you can block the
So you don't actually use the slit of spotlight. Okay.
yeah. So we'll have to actually, maybe that's a slide that I should have talked about a little bit. Sorry for skipping. So this is a SpUpNIC slit box. It's a very bulky thing. So we have to check this, but we can take this out so that, and then feed the fibers. So it's easy to remove. And yeah, so this is one of the things that I checked when I was at the telescope, and Lisa was also there. So we,
So you're not going to open a slit, you can take that ultimately.
yeah.
So
So
the two slits will have a lateral offset about 40 microns.
and the slit also box is just not a slit, it has some optics in itself. So that also we'll have to include on our, so there's a lens immediately after the slit. But we'll have our own new lens in the expander that we are making. So basically, I mean, we are doing everything that is needed to completely replace it optically and mechanically.
Well, the optics in that slit, is that for the actual spectroscopy, or is it for power acquisition?
No, it's just it's for a spectroscopy. It's a field flattener, very low power lens. So yeah. So that's the small lens that you see here, somewhere in between. So basically, we'll have an exact replica of that lens in our system, so that again, when the beam comes out of the entire system, it's the same as SpUpNIC gets it after the slit mask, after the slit box. Does that make sense? Yeah. So yeah. So just to summarize the information, the design is such that we'll get, I made it 656. It should be 454. So anyway, the field of view for polarimetric mode would be 20 by 10 arcseconds. And for non-polarimetric mode, it just double the number of fibers. And in this particular orientation, why is there no number? It should be 27 by 20, actually, 20 arcsecond, XY dimensions. We're using 100 micron fibers for now. As I said, if needed, we can go for 50 micron fiber in another iteration. But for now, it seems fine. And based on the F number, each fiber corresponds to a 3.2 arcsecond circular field. So it's not going to be seeing limited. The median seeing at SAAO at Sutherland is 1.5 arcsecond. So it's not going to be seeing limited, but since we are mostly interested in extender objects, it probably is not a big limitation for us. And yeah, so the physical dimension of these bundles will be really small, actually. So for the polarimetry mode, it will be 0.4 by 0.8 mm. And for the non-polarimetry mode, if we go with this configuration, it's going to be somewhere around 1 mm by 1 mm. Yes. And yeah, I started with optical design, but of course, optics doesn't float in air. We have to build all these mechanical systems so that they are held with us. The entire optical system is held accurately and sturdily. So this is the overall optomechanical system for SpUpNIC. Ignore this top thing on the right. I could not get rid of it in the.
That is floating.
That is floating. Yeah. But yeah, so this is all the optics, and so all the optics is now as covered or mounted in their mounts and assembled together. So this is again every component that you see here, apart from the base plate, which is SpUpNIC plate. Every component that you see here off the shelf Thor Labs commercially available, and uses this cage system that's easy for mounting and alignment. So I'll just go through some screenshots of how this works. So from Zemax, we get this set of lenses for the reducer, right? Lenses and mirrors. Then we start putting the lens mounts. Then we start putting any accessory mounts. Then we put other mounts. Then put the half-wave plate rotator at the top, and then you start putting case system. So this is a sequence in which it will be assembled in the lab. Yeah. And same with the expander. We have some lenses that we get from Zemax, start their mounts, putting the mounts and accessory mounts, and then start putting case systems. And the expander will sit on the base plate, and then on top of that, we'll have the reducer, and yeah, this entire optical system. And then this will go inside the SpUpNIC box that I showed you, the first slide. Not first slide, but somewhere. First about FiberPol. So basically, we wanted to see that this will fit inside the box of SpUpNIC, and it fits. We had to carefully check that, but it fits. Yeah. So that's more or less the overall design top level of FiberPol. Other questions here? You can take.
How do can you measure the polarization of specific for specific mode and the spectroscopy mode? Then, for example, I want the polarization of a specific wavelength. How do I get it?
So, sorry, I should not be doing this. I should be doing something else. So, the output that you will get is this is the output we'll get. Polarization as a function of wavelength. So I said polarimetry, but what we're doing is spectropolarimetry. So Stokes parameters I, Q, U as a function of wavelength. So that information will be there. As a function of wavelength. Does that answer your question?
So you think the light in terms of wavelength in the
No, so yeah, that's a good point. So the light splitting based on polarization is done by FiberPol. The SpUpNIC instrument is built inherently that it can split light based on wavelength, which is spectroscopy. We are just ensuring that before it's split as function of wavelength by SpUpNIC, we are separating or segregating the polarimetric information. Right? Yeah, sorry.
Since you share this study, and I'm wondering how well with the wavelength range that you have can you explain that once.
Usually the peak is around 550-ish.
But it's so not sharp, right?
It's still reasonably sharp. I mean, people use broadband filters to do this, of course. That's not, they do it because for lack of better data. But I think if we reach up to 400, I don't think we'll have any trouble. As long as we have enough data points, either side of the peak.
400 to 700, 400 to 700 is sort of a bottleneck. I mean, you want to advertise this to other spectrographs. If there's a graph in the range, you second,
Yeah, maybe I should tell why we got stuck with 400, 700. We're using commercially off-the-shelf optics. Commercially off-the-shelf optics come with standard coatings. And standard coatings are optimized for 400 to 700 or 700 to 1000, something like that. It's either or. And since this kind of peaks at 550, kind of at the middle, 400 to 700 seem like the right place to start off with. Yeah, that's the basic idea.
One is something that, more than an octave, you would have to do that.
Yeah, that would have.
But the optics still is, I don't know if you mentioned, I mean, what's the largest optic?
Yeah, I'll come to that. The largest optic is 1 inch. So, this.
That's also on the all science
Right.
And I think stuff detected will probably be more technical in there as well. It's not particularly easy to detect it, I think. Well, I know what the science I do before
Right. I mean, yes, that is true. I mean, if we had more resources at our hand at this moment, and this being technology demonstrated.
Yeah, Nick just asked that, so you have to choose. You either get something that's optical or near infrared optimized. And so we made the choice for the prototype for the optical. So there are certainly options in the future to get something that's red near infrared optimized, or to pay more money and get a custom very broadband multi-layer AR.
When you already purchased.
Yeah. This gentleman. But it's, this is just a specific example of things that 500, but to each overlay.
Usually everywhere it's 550. That's one of the interesting parts of Sikorsky curve that we get. In diffuse ISM, it's usually always centered around 550.
So what if the dust grain size of things? It's like double the size of each I mean, you measure dust grain size basically with so the grains get double the size of each shift like fraction or a couple of nanometers.
If the smallest dust grain that aligned with the magnetic field doubles, this will shift by double. It's just that it doesn't happen. If it happens, of course, that will be a discovery.
Yeah,
but we'll know, right? So I mean, this like with the best knowledge that we have. I mean, there's nothing right now that tells us that we should be expecting twice the size in LMC than what we get here. So it's just starting thing to see what's happening there. How much does it match this? I mean, of course, if it's double, then we will know it's double and then probably make the instrument throughput more optimized for red wavelength. We don't have this information.
One more technical question. I mean, I didn't realize you were going to do this. I mean, it's not just a mechanical thing, but you find wires, that.
There is just one mechanism, as in some wire to just move that mechanism. And as I said, there's an optics inside, small field corrector lens. So
So that's I mean, feed through, you know, through these wires unpluggable, or is it?
yes, it's just remove and connect, plug in, yes, that kind of system.
Yeah, sure. It won't be wire.
Yes,
Right, so it's close to the wires. So, I mean, this is, as you explained a little bit, it was derived by measuring the polarization of the background stars that's going through the intervening dust.
right.
But if you're going to do polarimetry of the galaxies, you're no longer measuring the polarization of background stars going through the dust. Like you'll measure the polarization of
It will have scattering.
there are lots, so that's not.
E-
Close to lots.
It will have other component. There'll be scattering component involved because I mean, it's not just direct, as you said, it's not just a background source. There will be some diffuse emission and there's some scattering, and there'll be different components. I guess it will also depend on what it target specific things. I mean, if we choose targets for nearby objects where we kind of know beforehand what kind of have some idea about doing the foreground and all that, that has to be taken, I mean, thought through and decided accordingly.
One of the reasons for the choice is the 4,000 to 7,000 is actually a throughput sweet spot for spotting. And there are great spectral diagrams, which are H beta and H alpha, that allow you to measure something about the bond. It allows you to actually correlate something in the ionized gas, which is giving you the total expansion and correlate that with the polarization. So it's a powerful combination. This waveline is probably a good place to start.
Oh yeah, and I agree to the other point that you made. It's going to be multiple components, and separating those out is challenge. And it's a challenge that we are kind of dealing with now, even with salt data. I don't know if you know, but with Koshas and Nikos, we are observing these faraway galaxies, and we're getting a spectropolarimetric curve, and that has multiple components. And our challenge is to extract out different components. And the good thing is that they have different wavelength dependence. So hopefully we'll be able to separate it out.
There's a question in chat. Nikos asked, thanks, how background suppression works. Do you need to go off the source and expose for the same amount of time for each science exposure? That's one question.
By the way, I'm not finished with all. Let me just finish it. I'm just worried that so Nikos, I'll come back to your question. Yeah, I'm just worried that I'll skip time. So we're already reaching 12. Where was I?
The current steps.
Right. Yeah. Yeah, so we have finished the design. The components have been ordered. It has gone through SCM, and Thor Labs is going to send us this set of components soon. I think everything is, apart from 2 or 3 components, are in stock right now. So beginning next year is when we will actually start putting this together in the lab, start testing and characterizing this in the lab, and then hopefully commissioning as soon as we do it. And hopefully, and I mean, it would be great if we can do it by the middle of next year, but we'll see. It's a kind of a unknown thing. Nobody has done it before, I think. So we'll see how that goes. But the aim is to commission it 2024, and it will be a demonstration of it. So when we do the first run, it will be technical as well as scientific demonstration. Scientific demonstration being do some science out of it, right? I mean, it's interesting technical exercise, but what would really make it even more meaningful is to be able to do some interesting science out of it. And yeah, if you have any science in mind, it would be great to just chat, and that can become part of the initial run that we do. So yeah, just a summary slide. It will enable integral field spectroscopy with or without polarimetry on the 1.9 meter. or 74-inch, whatever you call it. As far as I know, this is the first 2D spectropolarimetric capability on an existing spectrograph in astronomy. And the good thing is, it can be used with any existing spectrograph. There's no requirement. We can use it with an RHS-like instrument or a HRS-like instrument. There's no dependence on the spectrograph type, as far as I understand, as far as I can think. And it's a very low cost and small size instrument in the sense that all the optics are 1 inch or less. And for example, all the components that I showed you cost around 10K USD, including spares. So we have gone all out in trying to minimize the cost as well. Yeah. What did I say? Yeah, and if we're successful, it can, as I said, it can be technology demonstrator for larger telescopes, because usually when large telescopes face trouble, polarimetry is the first thing that they get rid of, because polarimetry is just technically and logistically a pain, because it requires large sensitive optics, including the large Wallerstein prisms, which are very difficult to handle and manage, and especially for salt. One of the troubles that is there in a calibration is that it's a moving pupil telescope. So depending on where the pupil is illuminated and subsequently illuminates a different part of the half-wave plate and polarize the optics, and that leads to variable instrumental polarization as a function of time and spatial location of the pupil. With fibers, because it's going to go through fibers and the fibers scramble up all the imaging information prior to it, a lot of that will get mitigated. So it will, if you just in the context of salt, if we do this kind of thing, it will make the calibration easier, instrumental calibration easier for polarimetric mode. Yeah, I think that's where I will stop, because yeah, it's already a lot of time and I've covered pretty much everything that I wanted. I had some slides on wall-up, but that will take another 10 minutes and I don't think we have that much time. So
Thanks a lot. Questions? Yeah.
All right.
I'll come to that.
Okay.
Yeah.
Can you comment on how long you envision this thing to be installed?
As to how long this will be installed in the first run or something, I think it will depend on how much science is there that we want to do. And also, I don't think it will be a year, at least for now. Probably will few weeks is at the first run, I think. That's the way it's campaign. And also how, yeah, I mean, everybody thinks that when they put an instrument, it will work without any troubles. We'll see how much troubles we have when you put it on sky. But of course, not a year, that I can say. I can't see how it will take a year.
Well, I mean, the point is that whatever we do, for instance, we mod a couple wires. To put this unit in, it will be put in a way that is straightforward to recover. And so we will go in and we'll probably start with a few campaigns, because how long can you stay at cell before you go crazy? And everything works great, and that's why people who have interest in using the instrument, it would be great to fold in your programs, because everything works in the first campaign. We'll try to take some science observations, and then people can assess whether this is a unit they want to have dedicated on there or not. But the idea is it goes on and it comes off and everything is returned, and no one's alive.
This is going on for the model or use this compared to now.
Let me put it this way. This system by itself will reduce throughput by around 80%. So by 20%, sorry. So there'll be 80%. It always makes something. So we'll get a 20% throughput hit with either you use polarimetric or non-polarimetric arm, including the fibers. So yeah. But I should add one more thing. I didn't talk about it, but another thing that my had initial seed idea about science to use would be asteroids and comets. They're heavily polarized, especially comets, because they have dust and the polarization changes as a function of phase. And if your outgassing happens, that different dust grains start coming in. So you get variations in polarimetry as a function of wavelength. So comets are one of the very interesting targets for this kind of a system.
Yeah, so will we be able to measure polarization from the hidden AGNs and clusters?
Which one?
So there are many hidden AGNs, and we also see that extended magnetic field structures in many clusters.
I think the limitation would be, even if we could do it, I don't, how bright are these? I think we'll be limited by 10, 11 max for this system. Most
Clusters are very.
Let's talk about it. I don't know. If they're bright enough, why not?
So it would be fine to do it on nearby AGN.
Sorry?
What would be the magnitude?
So it'll be somewhere between 11, maybe max 12. I don't think we'll be able to go beyond 12. But that's 12 per fiber. So if it's an extended source, it's a different thing. I'm just thinking in terms of a point source. If you just observe a star, probably 12 max, maybe 11 actually. Spectropolarimetry. I'm not talking about spectroscopy at this point, because polarimetry, as you know, we get, if the signal is 1%, then we lose 9-10% of the light just because of noise. So that's 5 max.
If the non-polarimetric mode, take whatever SpUpNIC currently delivers and not polarimetric.
So
You were saying polarimetric mode is 12 and
that would be my anticipation. Maybe 11 or 12 would be optimistic.
most of the lasers are out.
Yes. That RSS is there for that. I mean, RSS can look very deep, right? So, yes, Steve.
So, little quick calculation. So the sky field input there, right? There's 3 rows, and they are 20 arc seconds long.
Yeah.
So 3 times 20 is 60 arc seconds, like 1 arc minute. If you did it 1 minute, right? It's a 1 arc minute by 10. Yeah. No, it's a 1 arc minute by a third of a 10.
So 20 arc second is the entire thing, not individual fiber, right? So, sorry, maybe I just got confused.
The sky footprint at the top is 20 arc second by 10 arc.
Yes, that's correct.
So it's effectively, if it was all lined out in one line.
It's 2 arc minute. 1 arc minute, because that's a slit length.
Yeah, I understand that. So, my question is, is it necessary to use fibers? Is there an alternative optical design where you don't have to use fibers and you keep the long-slit, because the long-slit is 2 arc minutes. So your argument at the beginning was in terms of efficiency of using a fiber bundle rather than using a slit in different, but the slit is 2 arc minutes. And the area, the total area on that is only 1 arc minute. So, I'm making an argument that.
So I think the argument is that you couldn't use 2 arc minutes, you have to use 1 arc minute, long slit. And then through mirrors and image slicing, you could then get 2, your E and O, 1 arc minute slits, and then remap them back. It would be sort of like an image slicer. The disadvantage is that your field of view for your expander and reducer would have to be much larger, because it would have to cover, instead of 20 arc seconds, it would have to cover 60 arc seconds. So it would be more complicated optically, and it would probably be lossier because you have more surfaces and these way more expensive. All of these, the image slicers are the sort of Mercedes of optics. They're very expensive micro optics, whereas the fibers allow you to. And then the question is, would you prefer to have a 1 arc minute slit or a 10 by 20 arc second array? And for extragalactic or for nebular spectroscopy, you prefer the TP array.
And just to add on that, I mean,
Sorry.
yeah, people have done slicer-based thing. I mean, I've seen they're trying to use this for exoplanetary work, low resolution image slicing, spectropolarimetry, but that's for very narrow field and exoplanetary systems. They've still not fully commissioned it, but they're trying to do it in Subaru. Sorry?
How is target acquisition of the system?
This is the one question that I'm not very sure the answer would be.
So we are retaining the slit here. Inside the system. So just to ensure that the light is actually going to be set. Here we go, sorry. The slit inside the system.
Yeah, but that's target acquisition.
No, that's pretty sure that we are actually seeing the light. But I don't know how you haven't planned for alignment yet.
So that, as I said, I have not yet. It's something that has bothered me, but I've not found a solution to it.
Yeah, I mean, if instruments like this with sharp there, it would be otherwise.
That's also crossed my mind. So it's something that we have to work out yet. I have not yet sorted out how we will do it. Nico's right? Yes. Let me see Nico's question.
How background subtraction?
Oh, right.
You need to go off the source and expose for the same amount of time for each cycle.
Yes, that's what we will have to do because we would be limited by brighter sources or brighter galaxies, which means they will be bigger enough that we won't get any sky inside our fiber bundle. So we'll have to do that.
Also, you mentioned that the wavelength is 400 in case you want to observe significantly restricted sources. You will be observing the viewer in part. Is there a room to play around with the wavelength range?
I think because if it's very redshifted, it probably even won't be bright enough for us to observe. So that probably anyway will place a natural cut even before it hits the instrument. So Nicholas will be limited to brighter objects, which probably would ensure that, for example, the targets that we observe with salt, we won't be able to observe because we need it to be brighter. And as the question is, there's a room for playing under wavelength range? Not for this version. Maybe for a future iteration, we get more money. Maybe we'll go with custom coatings and that can do that, but not for now. Yeah, I don't think there are other questions.
So I have a question for the polarization community. So right now, Siddharth showed you the slit, which has the E&O bundles mapped into segments of the slit. Intuitively, is that what?
This one?
Yeah, would that be what you would do, or would you interleave the fibers so that every other fiber is coming from the E&O bundle?
So all fibers correspond to the same part on the side instead of look at it as separate part of this.
No, it's not necessarily software only. It could be, for example, if the E&O fibers are just side by side, you could potentially run into the problem that if the traces kind of mix with each other, then they will start contaminating. But the advantage is that they will follow nearly the same optical path through SpUpNIC. So calibration might become easier, photometry might, extraction might become harder, polarimetry might become harder. It's something that maybe I should ask Ram as well.
I think what we need to do is incredible simulation of how much the optimal gap is for.
If Ram is there, maybe I can ask him. I don't know if he's there. His thoughts on this. Yeah.
So with these 5 chunking fibers, with the like 3 arc minutes, right? Which
3 arc seconds. 3 arc seconds.
3 arc seconds. Which of the gradients still makes sense to use? The high resolution gradients you want to bother with, right?
Yeah. Especially for the science that we have in mind for polarimetry, we just need.
For anything, I mean, if you're not getting the resolution anyway, why would you have to use the?
So get more or less higher. really depends. You do have a wider slit, that's right, but, you know, if you use a higher resolution grade, you'll still get higher resolution. So it just depends what resolution you get. Yeah, I mean, what people probably use for a second slit.
Oh, sorry.
You throw out light.
Well, I mean, the seam can be 1.5, between 1 and 1.5. So on a really good seam, you bring it down to 1.5.
Right, so you tell the slit width, depending on the seam, on this, then if you want better spectral resolution, you give them the slit width, change it.
The point is also to demonstrate that. So if you had to design a song, there are those limitations you could make.
Start with the positive description. So we didn't go through the smaller fibers because we're still trying to get was right now to make the holders for 50 micron fiber, I think 100 micron. The 50 micron fibers are really a challenge for the shop. Could do it, but we thought this was the safe place to start. And if the net outcome from the first campaign is everyone loves it, they want the fiber size, then all we have to do is rebuild the fiber plug, and that's pretty cheap. So, you know, the $10,000 and all that FiberLab hardware is all the same. All we do is we put in the cable.
Talk about wavelength calibration?
No, I didn't talk about it, but there is. We'll use the existing arc that is there on SpUpNIC. The lamp, thorium lamp. We will feed it at the top of this thing. Let me come to the optical design. So this fold mirror will, although it's there to switch between where is it? Switch between the polarimetric and non-polarimetric one. It can also, you can imagine a situation where we'll have to route through a optical light guide, the light from the arc lamp, so that it falls on the other side and gets fed to the system. So before the fibers, we'll have to inject. So that's another thing that we have to mechanically sort out, how we will guide the light. But that's the plan. We'll, yeah, that's a plan to do it. Maybe for low resolution, if you're looking at 500, maybe skylines may be okay, but we don't know.
Even if you want to do polarimetry, you don't want to go wavelength hardware to a reasonable accuracy. We should get a proper polarimetry measurement.
Yeah.
Match it with polarimetry.
Yeah.
No, I mean, the plan is what I said, is to have a linear file to do it like that. Fold flat, where the top folding.
The same polymer will act as a selection for a converter. They also highlight and have beneficial.
But instead of feeding the current log maps, you know, such a limited mode, only this range, only these ratings, not really just getting on glass or settings.
Aren't they expensive? I thought they would be expensive.
I think a little bit like that.
I mean, if it is that feedback to life like that, we haven't gone into details of like it.
And you want quartz too.
Yeah.
I mean, why reinvent the wheel if you have a cap?
Yeah, I mean, and we looked at the hot maps and the closures on big fire in there. It seems like just saying it's easy, but actually.
Yeah, so I said that's one part we have to sort out. But as Matt said, we want to use as much as available without trying to invent and invest as well. So at this point, it seems like rerouting the arc lamp might be the easiest option. So, but we'll have to sort that out. As I said, we have not yet sorted that out. That's one of the to be done item. Yeah. I don't think there is any more.
Yes. If not, it's, thanks a lot again.
Thank you. I'll stop sharing. You've recorded this, right? Yeah, okay.